Hello viewers, welcome back to the course on scientific computing using MATLAB. So in the previous lecture we have tried to make some MATLAB codes for the given methods whatever we have discussed in this unit. So today I will give last topic in this unit and then we will start with the numerical differentiation. So today I will give you that suppose how we can extend the least square line to the data of different type. So suppose we have the data points, so that data points are distributed in the given x or y coordinates. So suppose these are the data points we are going to have. Now if I approximate this one with the least square line, so our least square line will be like suppose this one, or it may have like this one, or it may be like this one. But from here if I find that the data pattern, looking at the data pattern, we find that this pattern can be approximated with a function which is not a line. It may be a function of this type, so like this one, or I can say that this is an exponential function. So the given, looking at the pattern, what we do generally what we do, first we try to plot the given data in the xy plane. So looking at that pattern of this one, we approximate the given using the least square approximation. So how I can extend the least square line to the function of different type. So that is the how we can do this one. So I will try to find what is the approximation by standard formula. So standard formula like this one in this case. So I take the case number 1. Suppose I want to approximate this with some exponential function. So a is to power bx. So this is my pattern, and looking at this pattern I see that okay, exponential function is fitting for this given data. So how I can fit a exponential function for the given data. So let us suppose this is my exponential function and I want to fit this one in the given data. So what I do is that I will take the taking log both side, natural log. So it is my ln y, so that is ln a e bx. So I can write from here, this is my ln a plus ln e bx, which can be written as a plus bx. So this is my ln y. So now from here you can see that I have transferred or this data that was exponential into the linear form. So I can introduce that let my ln y is equal to capital Y, my ln a is another constant, I call it capital A. So from here equation 1 can be written as y is equal to a plus bx, and that is the equation of a line. And this equation of a line, we know that how to find this equation of a line using the least square approximation. So using least square line we can find the coefficients capital A and B. So once I know the value of capital A and B, I will put the value of capital A here and I will find the value of A by taking the exponential and taking the capital Y, I am taking this Y. So, once I know that this value, then ln y will be capital Y. So, from here I will e raised to power y. I can find my small y, so that is e raised to power capital Y. Similarly, I can find ln small a, that is equal to capital A, and from here I can find the value of a, that is e raised to power capital A. So, once I get this value, I am able to find this, and that is my linear approximation. So, based on this one, for the given exponential function, I have converted that one into the linear form. So, that is called the linearization of the exponential function, and using the method of least square line, I am able to find this one, and then I will able to solve the equation number 1. So, once I having the value of a and b, then after the finding values of small a and b, because small a is there and b is there, I am able to find my exponential function y is equal to a e raised to power bx. So, this is the way we can find. Now, based on this one, I am able to find my approximation of the exponential function. So, this is the way we can find out. Now, I define the case 2. Let my pattern of the given data is satisfying the function of this type a x raised to power b. So, in this case, the same again, taking log both side, I will get ln y is equal to ln a plus b ln x. Now, from here I will write this y is equal to a0 plus b x, where a0 is ln a and capital X is ln x and capital Y is ln y. So, once I get this value, this is the corresponding line I am going to have. Then using the again the same as the least square line, I will try to find value of a0 and b, and based on this a0 and b, I will try to find the value of a and xy, and then we can find out this power function using the least square approximation. The same way I can define the another type of pattern. So, case 3, y is given to of this type. So, b raised to power x, like exponential function. So, in this case also I will take the log both side. So, it will be ln a plus x ln b. From here I can write y is equal to a0 plus b0 x. So, again based on this linear approximation, I can find the value of this coefficient a0 and b0, and then from here I can find the value of a and b. So, that a and b is now known to us. So, based on this one I can find out this approximation. So, in this way we can find out different approximation. Maybe I can take case 4, let I the data pattern of this type, suppose a0 plus a1 x square plus a2 x4. So, this is the 4th order polynomial. So, in this case what I do, let I put x square is equal to x. So, from here I will get y is equal to a0 plus a1x plus a2x square, and that we know how to find this one. So, this is a parabolic fit, and we have also discussed that how we can approximate this parabolic function, and based on this parabolic function I can find the value of a0, a1 and a2, and then I can approximate this function. So, just taking the small substitution, we can take the help of least square approximation for polynomial spline or linear or parabolic, then we can find the exponential fit or power fit for different type of data functions. So, that we can do with the help of least square line. So, this is all about the unit related to the interpolation. Now, we are going to start the next unit, and the next unit is numerical differentiation. So, let us we try to find out that how we can take the help of numerical differentiation. So, numerical differentiation is that, now suppose I have the data, and based on this data, suppose this is my data I have. So, let us I take the interpolating polynomial from here, or maybe a cubic spline. So, suppose this is my interpolating polynomial, okay. And suppose this data is satisfying some function. So, suppose this is a function of this type. So, this is my function. Suppose I take this function like this one. Now, from here I want to find the value of the derivative at this point. Suppose I take this point. So, this is the point x I am taking, and I want to approximate the value of the derivative of the function at this x, or maybe I can choose this x, or I can choose this x. So, all these points I do not want the value of the function, but I want the derivative of the value of the derivative of the function. So, in that case we have to take the numerical differentiation. So, in this case also we have the value x0, x1, x2, x3 and xn, and the corresponding y0, y1, y2, y3 up to yn. So, based on this data I will make a interpolating polynomial or curve fitting, and based on that one we will try to find out the value of the derivative at any point x in between these data points. So, that we are going to do with the help of numerical differentiation. Now, from here if you see that at the nodal values, this is my function. So, that is the function f x, and this is my interpolating polynomial. So, I call it maybe p x. Now, from here you will see that at the nodal points the actual derivative is this one, but approximating derivative is this one. Actual derivative at this point is this one, but if I approximate it with the interpolating polynomial, then this is the derivative here, this one. Okay. So, the same thing is happening here, actually this one and approximating is this one. So, you can see that there is a very big difference between the derivatives at these nodal values, because here you can see that actual is the positive one, but the approximating is the negative one. Here the actual is the positive, but approximating is something like a parallel to x axis or negative value. So, from here you can see that we can say that the interpolating polynomial p x oscillates about the curve f x. that we know, because the interpolating polynomial has all this nodal value as the root. So, that is why it will interpolate like this one. So, it will oscillate about the curves. So, in this case I can say that the errors will be quite large in the case of derivative. In the case of derivatives. So, now based on this one, so how to try to find out the value. So, suppose I have somewhere x here and I want to find what is my P2 derivative at this x, P2 or maybe Pn, I should define this as P. So, this is my interpolating polynomial and I want to find the value of the derivative at any x, this one. So, now in this case we will take the help of the previous unit. So, let us try to find out this one. Now, to find the value of the derivative of the function at any x belongs to x0 to xn. So, this is the point value is given to me. We try to use the interpolating polynomials and then taking their derivatives will help to approximate the derivative. Okay. So, let us try to take this one. So, let us take the case 1 when the nodal values are equispaced. So, let us try to find out this one. So, in this case I have my x0, x1 up to xn and they are equispaced. I have the value y0, y1 up to yn. Now, somebody asked me that give me the value of x, the value of the derivative of x for the x lying here. So, in this case we want to find the approximate value of derivative at x in the upper part of the difference table. So, this is the way we can find the difference table, and suppose this is the value I want to find the upper half. So, I know that. So, we can approximate first we can approximate the Newton's forward formula for interpolating polynomial. Right. So, now we know that I can find the interpolating polynomial. So, let us I will take x is equal to x naught plus p h, where h is constant. So, in this case it is given to me Now I can find my yp, the interpolating polynomial, that is given by as y0 plus p forward plus p minus 1 by 2 factorial p minus 1 p minus 2 by 3 factorial and so on. So, this is my interpolating polynomial. Now, I can write my p as x minus x naught by h, right. So, from here I can find the derivative dp by dx. So, dp by dx will be 1 by h. Now, I can find what is dy by dx. So, I can find my dy by dp, because y is containing this p and this will be dp by dx, and dp by dx is 1 by h. So, from here I can write 1 by h dv by dp. So, this is a y function, it is a function of p. So, I can take the derivative to this one. Similarly, I can define second derivative. So, from here I can define by d by dx. So, 1 by h dy by dp. So, this will be again equal. So, I will write d by dp 1 by h dy by dp into dp by dx, and from here I will get 1 by h square. So, that will be d square y by dp square. So, this way we can find any derivative. Now, from here differentiate equation 1 with respect to p. So, that we can find out. We can differentiate the equation 1 with respect to p. So, now I will get my du by dp. So, my du by dp will be what? It will be y naught plus then it is p square minus p. So, it is 2p minus 1 by 2 del square y naught plus, again I can take the derivative of this one. So, it will be p cube minus 3p square like this one. So, I can take the derivative. So, it will be 3p square minus 6p plus 2 divided by 3 factorial y naught and so on. So, this is equation number 2. So, based on this one I can find what is my dy by dx. So, at the value of x, so this can be written as my du by dp into dp by dx. So, from here I can write 1 by h forward plus 2p minus 1 by 2 del square y naught plus 3p square minus 6p by 2 plus 2 by 3 factorial and so on. So, based on this one I can find the value of the derivative directly from here. So, I put the value of y, I put all these difference values here, putting the value of p, whatever the p value we want to, we can choose from there, and multiply by 1 by h, it will give you the value of the derivative for the given x. So, using this one I can write this as 3. So, from equation 3 we can find the value of derivative dy by dx for given x, and that is x naught plus ph. Okay. So, then using this one we Newton forward methods we can find out this one. So, the same way we can apply similarly we can apply Newton's backward formula for the value x lying in the bottom of the difference table, and central formula, Stirling central formula for x lying in the middle of the difference table. So, and that we already know that how to apply this Newton backward formula or the Stirling central formula. So, once we find this Newton backward or central formula, we can take the derivative of the corresponding interpolating polynomial, and then we put the value of p in this one, and then we can find the value of the derivative there. So, in this case we have just to repeat the process for finding out the interpolating polynomial, and then we can take the derivative just to get the approximate value. So, in this case we are not going to repeat this again and again. So, this is we have done for the case when the nodal values were equispaced. Then the next case is case 2, when the data is not equispaced. So, if in this case if the data is not equispaced, then then we know that we can apply Lagrange interpolating polynomial or Newton divided difference formula. So, in this case, suppose I apply the given for the given data I apply the Lagrangian interpolating polynomial. So, I know that suppose I have 3 points. So, I have the polynomial maybe x minus x1, x minus x2, x0 minus x1, y0. Suppose I have 3 points x0, y0, or x0, x1, x1 and x2. So, in this case I will find out this polynomial x2 minus x0, x2 minus x1, y2. So, I will get this polynomial, and that is a polynomial in x. Then I can take the derivative of this one, taking derivative. So, that will give the p dash x. So, from here I can approximate the value of the derivative for any x lying between x0 to x2, or similarly we can find derivative of the Newton's divided difference formula. So, in that case also we are getting the interpolating polynomial, and then I can take the derivative with respect to x, and then we can approximate any value of x in between x naught to xn to find out the value of the derivative for the given x. So, this way we can find out with the help of the interpolating polynomial that we have discussed in the previous lecture, we can find out the value of the derivatives, first derivative or the second derivative of any value of x lying in the given values of x. So, that is x from x naught to xn. So, I will stop it here, stop today. So, today we have started with that how we can apply the standard formula for the least square lines, and then we started with the numerical differentiation. So, with the help of the interpolating polynomial, we can find out the value of the derivative for any x, find any x lying between the datas. So, there is no need to do to repeat this again and again. So, we will continue with this one in the next lecture. So, thanks for watching, thanks very much.